Hello, welcome to this installment of Swift UI for the old school guy. I'm going to discuss the topic of runtime versus compile time polymorphism. If that makes your head spin, I invite you to go on this journey with me. Thank you. The times that I've done professional training and used the phrase compile time versus runtime polymorphism, a lot of eyes just glaze over. And I'm like, okay, I need to start from the basics with this. And in this video, I'm going to kind of demonstrate the same problem being solved given those two forms of polymorphism and why you would want to use compile time when you can. Okay, so to begin with, polymorphism is when you have differing behaviors depending on your different types, and you have kind of one reference to that type, where most of us are familiar with inheritance with virtual methods. Compile time polymorphism is when you can, at compile time, swap out the different types, and that's mostly implemented using type generics that most languages support. So I'm going to have a contrived example here with a contrived requirement that there shall be no hissing in production. We begin our example by declaring a protocol, which is Swift's keyword for interface, called cat. Now we're going to make two swipes through this code, one concentrating on the runtime implementation, and then we're going to come back and look at the compile time implementation to compare. So cat has a polymorphic method called per, and it takes an owner of any kind, and it will return a string. And all classes that adhere to cat must have an implementation for this method. It's just like in Java and C++ or any other language with abstract virtual methods. We have a do-nothing class called human as our owner. You may know some humans that do nothing, but that's a whole nother discussion. Then we have an extension on cat. Now, extensions is a very nice language feature that lets you add methods to existing types. So let's say you have a third-party framework that you wish you had some convenience methods attached to it. Well, you can use an extension to say, okay, this method now is part of that class. It also allows you to have default implementations for protocols, and that's what we're doing here. So the default implementation for anything that's a cat, his per function, returns either the string per or his. Now, there's a couple important things to note here, is that we have type erasure going on. So even if we had a protocol for owner types, we would still have type erasure at compile time, because at compile time, we don't know the exact type of owner it is. So we have to make runtime decisions like checking its properties or checking its type. And since it's a runtime decision, it can fail, either throw an exception or return a hiss. And since this is more code and more code has possibility of more errors, we actually have now a typo that we have to take care of. So this adds testing overhead. This adds runtime overhead that we don't necessarily need, but it works. And then we skip over compile time. So we have our first cat type, which is spoiled indoor cat. By the way, for me, that cat's name is Whitney. I think there will be a picture at the end of this video. And well, Whitney inherits the default implementation. If the passed-in owner is human, she purrs. If not, she doesn't. And then we have a feral cat. And a feral cat here has to override the function because it can't use that default implementation. Feral cat always hisses, always. But the problem is we have a mandate of no hissing in production. And since this is a code path, if there's a function you have in your code, it will get called. Now that we have our two types of cats, we then go inside of our application where we present to the user the information derived from our business logic. So we have a spoiled cat, a feral cat, an owner of human type, and an owner of empty tuple, which is an empty structure, basically. I'm using that to mean no owner at all. So we have hissing in production, unfortunately. So if we look at the code here, or the output, we have our success case, our happy path, which is spoiled per with human. But now we have the unhappy paths. And since it's code that can be executed, it is being executed, which means we have to check for errors. That's why we turn it to red. But we also have our typo shown up too, which can be rather embarrassing. I've done that before in production code. It's embarrassing. And so then we have all of this logic here. Okay, but it works. We've been able to detect the error. We present the user the success case. Oh, very good. But that's a lot of code distributed amongst a lot of classes. So if we go all the way back up to the top and go back to our protocol, we skip over the runtime part, which we don't use anymore, and we create an associated type called owner. So in Swift, how you add generic type parameters to an interface, to a protocol, is the keyword associated type. Other languages would denote it up here with a different syntax. But now every cat must declare what its owner type is. We still have our do nothing human. We don't have this function at all. But now we have a different version of per. We're still in our extension, which means every cat inherits this. If we pass in an owner type, so this is a generic type parameter for this method of type O for owner, and what we're saying is that owner has to be the same thing that the owner type is declared in that cat, and the owner type has to be a human. If these two compile time checks pass, then we return per. Great. Simple, concrete, and there is no hiss. So if we look at cat, he inherits this non-runtime polymorphic method, and he declares his owner type of human. And feral cat, he doesn't have to declare hiss anymore. He just says his owner is the empty owner as well. So we skip over the content view runtime, and then we go to our content view compile time. We still have our four types of objects, but now the difference is we have a singular case of cat1 to owner 1, because these other three cases are now compiler errors. So if I uncomment this line, wait for it, and it says it needs to be human. Okay, well, then we comment out that line, and then we have this one, which is and that type needs to be a feral cat owner. So those are our two type constraints. And the third case is the same as the first failure. So what we've done here is we've eliminated the entire error case out of production. As in, you can't even compile if you are not purring, because there's no hissing in production. It's pretty much you're purring or you're not compiling. Now, the additional benefit of this, besides reduced code, reduced testing, um, is that the optimizer can come along here and look at the code and see that, wait, the only case for this string inside of the entire application ever is per. No, not that per, this per. And then once it does that, all of this other logic just can be optimized away, including the Swift UI auto-generated reactive code, because now that 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 string, that singular case string, is non-reactive, it's immutable, and it can be compile time computed, which hopefully the optimizer will come along and at compile time compute this string, because it can through its own analysis figure out everything's constant. So overhead of both computation and the Swift UI object graph and all of this just gets greatly reduced. Our testing is reduced. Our code spread is reduced. So hopefully, given these two examples of runtime decision versus compile time decision, you can see some of the benefits of thinking about, can I solve this problem with the compiler? Now, there are many other benefits to using compile time decisions. Swift UI, in fact, demands some of that. So thank you for going on this journey with me. See you next time.